Myself is Animesh Singh. I'm a chief architect for data and AI open source platform in IBM. He's Clive Cox, CTO of Seldon, a company based out of London, doing a lot of great work around model inferencing and model serving. So today we are going to talk about, in general, introduction to machine learning and the challenges, specifically in the context of model serving and the challenges we face there. And then, once you have served your models or deployed your models, how do you actually monitor it? And finally, wrap it up with some summary and description. This is a quote which you probably would have seen, many times over, right? It took me 3 weeks to develop my model, more than 11 months, and still not deployed. A lot of people think it's exaggerated, but this is, it came out of one of our VPs, and actually, talking to customers, that's the comment we heard, right? And we are surprised how much it resonated with a lot of folks, right? That essentially that's the case. And why is it the case? Because the general perception is that ML code is the biggest part of your machine learning infrastructure. In reality, it's a very tiny part, right? A lot of efforts are spent around data collection, verification, process engineering, model serving infrastructure. So spend a lot more effort surrounding that ML code than in the ML code itself, right? And what is happening in industry in general is that to handle this end-to-end ML lifecycle, starting from data preparation, which includes data cleansing, data ingestion, data analysis and transformation, validation, and then going through the whole model lifecycle, which is building your models, training your models, validating, deploying. A lot of technologies are emerging to actually condense that, right, and make them faster to take you from step A to Z much faster. So essentially, a lot of us are now doing end-to-end machine learning on Kubernetes, right? And to do that, you can become an expert in a lot of these things, containers, config maps, secrets, GPUs, a lot of things which you are hearing in this conference. Or if you want to bypass a lot of that, then you can use something like Kubeflow, right? It's an end-to-end ML platform being built on top of Kubernetes to take away the pains, right? So that you're not required to be a Kubernetes admin or a Kubernetes expert to be able to do end-to-end machine learning on top of Kubernetes. It handles all the phases of machine learning lifecycle, right from building your models, training your models, deploying your models on different, model serving infrastructures, and then, tying them all together through a pipeline. So if you are into distributed training, there is a project in Kubeflow umbrella called Knative. Plus, there are distributed training jobs for TensorFlow, PyTorch, XGBoost, Chainer. If you like Horowitz approach of MPI-based training where weights and gradients are synced on a more peer-to-peer basis, that's supported as well, right? So distributed training at scale is supported through Kubeflow. Kubeflow pipelines, right? As I mentioned, there are multiple phases in end-to-end machine learning where you actually go from the process of, taking your data, cleaning it, and then going through, creating your models, training it, deploying it, managing it. Kubeflow pipelines essentially, allows you to do all these steps in a single consistent way. So it's a sequence of ML tasks, each backed by a container. So it allows you to go from step A to Z, but that's not the only important part, right? Apart from growing from A to Z, when you actually want to trace back the lineage from Z to A, that my model was trained on this particular data set, on this version of TensorFlow, using these hyperparameters. It was validated using these libraries, deployed, and these are the scoring characteristics. A lot of their data you can actually find, using Kubeflow pipelines. So whole metadata tracking and lineage is enabled. IBM and Seldon both are major contributors in Kubeflow, right? IBM is the second largest contributor over the course of last year. We are contributing heavily to Kubeflow, but the community is strong and very big. A lot of great work is coming, from Microsoft, Seldon, Cisco, Aricto, plus AWS. A lot of companies have now started contributing, and this community, as you can see from this chart, is growing heavily. And come January 2020, we are actually going to launch Kubeflow 1.0, right, which is focused on 4 major COJs, where essentially we want to make sure that our develop, build, deploy, and training lifecycle is total, stable, it's performant, and we are able to actually introduce a lot of features around user authentication, authorization, multi-tenancy as part of 1.0. So now let's get to the context and talk about production ML model serving. Why is it typically hard, right? So some of the problems are more generic in nature, right? So things like is your infrastructure underscaled or overscaled, right? Can you monitor your deployed models? Are they healthy? Can you roll out a new version of the model if things go wrong? Can you roll back, right? Can you actually swap traffic without changing the infrastructure and the deployed models? How can you actually do a generic prediction using different protocols, HTTP, gRPC, etc.? Now, when you move more to the model-specific world, right? General problems like I want to serve TensorFlow models, PyTorch, scikit-learn, XGBoost in a consistent way. Single spec. I don't want to write different sort of clients to deal with different kinds of models, right? And once the models are deployed, right, can I explain the model predictions? Can I detect concept drift? Can I do bias detection? Can I do adversarial detection? Can the model explain its predictions? A lot of these problems which are very specific to the model deployment world, right? And another thing which is very common is custom pre-processing and post-processing code. How do you actually handle, because your models are essentially dealing with tensors in, tensors out, right? What an end user is sending is probably images, text data, right? So a lot of times, in fact, most of the times, you'll end up writing custom pre-processes and post-processes. Can that be supported? So I think different parts of these problems were being done by different teams. At last KubeCon in Seattle, we gave a talk, how to use serverless inferencing using Knative. Bloomberg was actually doing great work on that side. Microsoft was doing a lot of work in terms of Azure ML on Kubernetes. Seldon was doing great work around model graph inferencing. And then Google obviously had been doing a lot of work around TensorFlow serving and optimizing heavily around it. So we were all solving different parts of the problem, and what we did was, over the course of last year, we all came together under one umbrella, under Kubeflow, and launched this project, right? And the goal was, let's work together. We are solving similar problems. Let's solve it consistently and drive towards a standard. We don't want more fragmentation in the industry. So that's how KFServing was born. And before I actually go, I would like Ellis from Google and Rakesh from Microsoft, just to stand up and wave. And Dan is here from Bloomberg. So these are, our co-conspirators. So definitely, 5 of us, or 5 companies, got together essentially to co-found this. And over the course of, last, I would say 7 to 8 months, this has become very popular. If you are following, Kubeflow in the last launch of 0.7, KFServing was the major release feature highlighted there. And our goal initially was to focus on 80% of the use cases initially, right, which is essentially single model rollout. And the key things which we wanted to focus there was the serverless characteristics, canary, explaining model predictions, and then being able to give you an ability to inject pre and post processing if needed. So that's how we ended up building KFServing. At the very bottom, we have our layers, right, the hardware layer, GPU, TPU, CPU. And then Kubernetes sits on top, and then Istio and Knative. And finally, with KFServing, right, we essentially strive to bring these multiple frameworks together, TensorFlow, PyTorch, Onyx, TensorRT, and then give a common set of functions around them. Being able to predict, right, get a request, get a response back. But going beyond that, being able to explain model predictions, being able to inject custom pre-processing and post-processing. Now, why actually did we choose Knative? One of the key things was definitely, the scale to 0 and the scale from 0 to n was an important feature. That was one of the core principles we wanted to follow as part of, model serving. It was our personal experience that over a period of time, these infrastructures become very huge, given that, model serving requirements are very, compute intensive, right? So something that we wanted. Another thing is, the queue or request queue-based autoscaling feature in Knative that lends itself nicely when you're actually working on disparate hardware infrastructure like GPUs, CPUs, TPUs, because traditionally CPU-based autoscaling can also be enabled in Knative, but when you have these different sets of hardware, it's not easier to actually be consistent. So I think request-based autoscaling works very nicely in this case. Istio definitely was needed. As I mentioned, canary was one of the key features which we wanted to support. So being able to do traffic splitting, traffic control, support canary deployments, and then also another feature of Istio which we really wanted to enable was observability, so being able to have metrics, logging, tracing, which we can use as part of the model serving infrastructure and then enhance and customize it for model serving. So this is how typical KFServing default and canary configuration looks like. Inference service is actually at the heart of this, right? It manages the lifecycle of the deployed models. One key distinction which you see here from Knative is essentially the concept of canary, right? So we actually have our own configuration for canary so that you can iterate multiple times over canary until you want to make it a default. And part of the reasoning here is that A, it lends itself nicely to GitOps. B, machine learning in general is very, very experimental in nature, right? The amount of iterations you will have to do in machine learning before you get to the final model which you want to deploy is very huge. So we wanted to make sure that we are not impacting the main revision of the default deployed model before we actually iterate multiple times on the canary, right? So that's one key distinction which we have here. As I mentioned, right, we support multiple of these model servers, TensorFlow, PyTorch, XGBoost, Scikit-learn, Onyx. And if you're following in general the Onyx ecosystem, Onyx is a way to actually standardize your multiple models, right? So if you have trained models using TensorFlow, PyTorch, Scikit-learn, you can convert into Onyx format and deploy. Onyx Runtime 1.0 was recently launched, plus just last week, Onyx moved into Linux Foundation AI in total open governance. So that's an exciting news for us at IBM and for the community. And we are actually also contributing heavily to Onyx as well. We support multiple different types of storage, GCS, persistent volume claims, Azure Blob, S3 compatible storage, etc. If you look at the control plane, as I mentioned, right, some of the key characteristics which we wanted to focus on was definitely enabling default prediction. But as the requests are coming, both for default and canary, we wanted to make sure that we are able to provide capability to inject pre-processing and post-processing. Hence, the introduction of Transformer, plus it enables us to do some intelligent routing in terms of taking the request directly to predictor or to explainer, and then from there to predictor, right? Once you actually deploy KFServing at your physical infrastructure level, it may look like this, right? We actually use Istio ingress for the external traffic coming in. You can also use your load balancer, if you want to configure like that. There are certain deployments which we have done, which you can actually use, external load balancer. And then Knative, the key things which we are definitely leveraging is autoscaler, scale to 0, 0 to 1. That's one of the key things. Explainer and predictor, if you see, once deployed, they look pretty much the same. One thing which you see here, which is again a little bit different from Knative infrastructure, is storage initializer. Models, machine learning models, they are very heavy. Typically, you have a lot of the weights and the graphs, right, which can become gigabits in size. And if you're actually downloading each of them from a remote storage at every time you are initializing your model containers, that can become a heavy cost. Right, so we introduce quite a bit of caching using storage initializer so as to be able to optimize that cost and bring it up faster. And another key thing which we have been doing is not only being able to deploy models in a standard way, but also being able to interact with models in a standard way. Because what was happening is that if you're using TensorFlow, you are using a custom protocol for pre-processing and or just to do request response. Same with Onyx, or if you are using Seldon, TensorFlow, TensorRT server, right? They all have their own data plane protocols. How do you actually send a request? How do you get a response, right? One of the key goals with respect to KFServing was also to make sure that beyond the standardization of the model deployment spec, we also focus on the standardization of the interaction with the model, right? So once you have written a client to actually talk to KFServing, get a request, response back, get an explanation back, you shall be able to use that same client, ideally, with TensorFlow serving, with Onyx runtime, with Seldon, right? So the idea was that, bring that standardization, and in V1, we have actually focused on a lot of these capabilities. Some, sample YAMLs in terms of, the standardization of the deployment spec. As you can see, around 7 lines. At the most, 7 to 8 lines of simple YAML to actually deploy scikit-learn, TensorFlow, PyTorch models in a very consistent, standard manner. There is no difference exposed to the end user, right, who is deploying these models. And then you can add, 3, 4 more lines into these specs and get canary and pinned rollouts, right? So in this case, for example, you see that we are specifying there is a default, there is a canary, and there is a 90-10% split between default and canary, right? So that's one of the key things which we have enabled as part of this. I do have a demo to show at this point. It's on my laptop, so I'll try and restart my laptop and flip. But until then, that happens, right? At this point, I will talk and pass on to Clive to talk about the next phase, right? Okay, you are able to deploy your models using a standard spec. Then you are able to interact with your models using a standard spec, right? So you're able to get to that point. Now that your models are giving predictions, can they be trusted, right? So are they vulnerable to adversarial attacks? Can you explain your model predictions? Is there concept drift, right? Is there an outlier? So Clive is going to actually dive into some of these production requirements, which we are hearing from our clients. With that, Clive, please go on.
Great. Thanks, Animesh. So yeah, I'm going to take you into he's told you about how to get the core model into deployment and how to do a rollout of that. But now we want to take it to the next level. What other things do you need to add to your core model to really get a robust production ML system? One of those is model explanations, and we'll go why you might need that and how you do it. Then you might want to also record your payloads as they're going through. If you can record the payloads, the requests and responses, then you can do things with them in near time after the model's made the prediction. So you can attach them to some technology like Knative and then push those payloads out to things that will give you understanding of what's happening to your model and give you metrics as to whether it's working well in production. Things like outlier detection will go into that, adversarial detection, and concept drift. So you can get a really good understanding of, is my model working as expected in production? So we'll go through those different stages. So why would you want to explain your models? Well, first, there's lots of regulation in Europe, GDPR, so people who are submitted to automated decision processes need to be able to be given some explanations of why they were given the particular predictions that they did. So that's obviously key for any models you're putting in production in those countries, and there's also regulation in the US in that area. Secondly, for the people such as data scientists and DevOps, they need to understand why is my model doing what it's expected to be doing. And if you want to actually investigate the actual behavior of the model on particular inputs which are unexpected, such as outliers. So all these are reasons why you might want to have explanations to give you a better understanding of what your model is doing for particular inputs. So what is a goal of a good explanation? Well, one is for it to be human interpretable. So you might have a deep neural network with many millions of weights. That's not going to be very interpretable to understand. So you're going to have to have a high level representation of what is happening in your model. But at the same time, you want it to be not too oversimplified. Obviously, you can have a very high level explanation, but if it's too high level, you're not getting a good understanding of what the actual model is doing. So there's going to be a trade-off always with explanations between something that's very interpretable or something that's very close to what the model is actually doing. So that's just one of the facts of life with explanations you need to take into account. So how do you do it? One is the core thing we're going to discuss today is black box model explanations. So here you're treating the model purely as a black box. That could be a neural network, it could be a random forest, it could be anything. There's input, so here you've got a set of features and demographic features, etc. And the model makes a prediction, in this case, to actually, say, deny a loan request with a high probability. And you want to understand why did the model make that particular prediction? So there's various ways to do it, and the core way that explainers do it, essentially, is you've got your model there, it takes inputs, gives a prediction. The model takes the same input, and it's going to change those inputs slightly, many times, for each of the features, and send it to the actual model, get a response back, and see how the model is changing its prediction as the features that you're actually sending to the model are changed very slightly. And that way, you can try to judge how the model is coming to its actual opinion about its actual prediction. And then you could turn all those particular predictions you made, which could be tens of thousands, to then turn it into human understandable explanation. So obviously, as you see there, it's going to be expensive. So you might have one prediction coming in, it's going to be hundreds or tens of thousands of predictions you need to send to the model. So we at Seldon have an open source library, Alibi Explain, which you can see the URL there, which is state-of-the-art implementations for different types of explanation algorithms, such as anchors, counterfactuals, contrastive explanations, and other things connected to explanations, such as trust scores. So that gives you, can you really trust the predictions coming back from your model? If they say high probability that they actually, this is true, is it actually the case that you can actually trust that prediction? So today we'll just concentrate on one particular type of explanation called anchors. So here you've got a representation of an image model, say ImageNet. It's got a picture of a cat, goes to the model, and the model says, okay, that's a Persian cat with 90% probability. So for anchors, it's going to find the core features, in this case pixels or superpixels, part of the image, that irrespective of what's around that, it's always going to give the same prediction. So here you run it through the explainer. It's obviously picked out the eyes and the whiskers of the cat. And irrespective of what happens in the image around that, this model will always predict that this is a Persian cat. So this gives you a core idea of what is the model actually focusing on to actually make that prediction. And so you get some insight into how it's doing it. So this is a version. Anchors has versions for images, tabular data, and textual data. And we'll take you through a tabular data example in a second. So how do you add it to KFServing? This is just a simple addition to actually your YAML that you do. You add an explainer section next to your predictor. You specify what type of algorithm you want. In this case, anchor tabular, as it's tabular data for this income model I'm going to show you in a second. And some explainers require some analysis of the training data to get some understanding of what is the likelihood of different features. So there's some explainers need to be trained, but that's not training on the model. That's just training on the training data to say, okay, this feature appears this amount of times with these values. So therefore, it can give you a response back that's easy to understand. So that's an example on the left for anchor tabular, one for anchor text on the right. So simply saying this is anchor text. I want an explainer for that, in this case for a movie sentiment model. So it's very easy to add. I'll go for a quick demo. There's two demos in the slides. I'll probably just go through the income prediction demo. So this is the structure that we've added to now. We've got the core model, and we're going to add an income explainer next to it using alibi explain, all deployed using KFServing. So we'll just go to the actual model here. So we'll have a look at the actual YAML for the actual model. What we're serving. So we've got the actual model at the top there, a scikit-learn income prediction model. It's based on the sort of census data from 1996. I've added a few things just to make it not use too much resources, and we add in the anchor tabular. So we'll apply that. Well, I've done that already, so I'll just go through some setup to actually get the IP address of the service and the service names. A few set up here, and we'll set up just some of the data so that we can send it to the model and get a explanation. Just wait a second for that to run. Could be the internet's going to fail us here at the last second. Fortunately, the other notebooks I've got already run. Okay, this is going a bit slowly. So basically, we can send two examples to the model. So here we've got some examples. This is the demographic features, say age, marital status, etc., occupation. And for here, it's predicting the person will have lower than 50K salary. This is from 1996. And here we've got a different set of features where it's predicting more than 50K salary for those features. And we can ask, okay, what is an explanation for why this first example, the one where you had low income prediction? So we send that to the explainer. That's going to call the model thousands of times. And it's going to say, okay, so what it's saying is of those demographic features here we had at the top, irrespective of what you check for the other features, if it's the person's marital status is never married and they're working less than 40 hours per week, you'll always get low income prediction for that. So therefore, you can look in that. That can give you a lot of insight. Maybe you want to look into that. Is your model biased in some way? Is it taking marital status, which it shouldn't be doing? Maybe you want to take that out of your data set. So you can all these things, which are obviously very important now to understand how your model is behaving. You could then get some understanding of your confidence in that actual prediction. So you can ask it for the actual precision. In this case, it's 96% precision. That means that 96% of the time, if those features just appear, the marital status and hours per week, your model will always give the same prediction of low salary. And then coverage says, okay, how much of the data set does this actually cover those features? So it's actually a reasonable size of the data set, 25% of the data set. And you can dive into how that goes down feature by feature. So if we add just the marital status, that will cover 32%, and then you add marital status and hours per week, that goes down. So you can give an idea of how much of your data set is covered by just these type of features and for what you wanted to do. You can do a similar thing for the high income example. I'll skip over that now just in terms of time. So it's very easy to set up, and that's how you add explanations. We're using Alibi Explain, our open source library. There's also a great library from IBM called AI Explainability 360, which you can also be used, and that will be integrated into KFServing in the near future. So if we just go back to the presentation. So next thing, so we've got explanations for our models. Next thing is payload logging. So why would you want payload logging? Well, for obvious reasons, you want to capture what's going through your model for future retraining of your model, and you want to perform near-time analysis of that model when the requests and responses. So we've added into KFServing an alpha feature, which allows you to add to any part of the KFServing description to the predictor, the explainer, or the transformer to actually log requests going through the model at that point. You can choose to log both the requests or the responses or both. And all you need to do is specify a URL of where to send those payloads. So that means it's very easy to connect to anything you want to do to connect it into systems. And we're using cloud events for this. So cloud events is a standard for wrapping your sort of event type data. So systems which want to work together on eventing can work together seamlessly, but with a standard set of headers in this case. It's a very simple addition to the actual payload, which is going to go through and be sent to allow various systems to work together. How do you add it to KFServing? You just add a logger section on the part you want to add logging to, give it a URL. In this case, I'm using the Knative standard service. I'm going to set up message dumper just to print out, but you could set up to push to like sort of alerting system or whatever you want to do, something that's going to save the data. And then you specify a mode. Do you want to log the requests or the responses or both? In this case, all. So again, because all you need is a URL, you can tie it into anything. You could tie it into Knative Broker and tie that into further systems like outlier detection and then push it onto alerting. Or you could tie it into, say, Kafka, have a Kafka bridge, and push it onto a Kafka cluster. So it's up to you, and it's very flexible on how you actually use it. So now we've got the payload logging, which is easy to add in. Then we can do some interesting things on really understanding, is my model working correctly in production? So 3 things I'm going to chat about is outlier detection, adversarial detection, and concept drift. And they all really come under the concept of you shouldn't trust predictions on instances which are outside your training data. So as your model may be trained a month ago on data, and the data coming into it may be completely different, and you shouldn't trust those predictions. And these type of techniques are trying to detect when those things are happening. So outlier detection is obviously when the data is not as expected for the actual model. There's many different types of that. Of outlier detections available. We won't go into all the details, but there's ones that are trained online as the data is coming through the system, ones that are trained on your training data, and obviously different types of outlier detection for the types of data of your model, and different types of outliers. It could be a global outlier, say something if you've got a model that predicts temperature, and it's predicting 1,000 degrees, well, obviously that's a global outlier, but it's predicting, say, 35 degrees in London in, say, December, that's probably a contextual outlier, because it's very unlikely at that time. And then you can have collective outliers, which apply to things like time series, where a whole series of events are together taken as an outlier. So another thing you want to do is maybe adversarial detection. So this is the case where people could be attacking your model with very similar instances, which are producing radically different outputs from your model. So here's some examples on the left. You've got something from MNIST, handwritten digits, where even though for us it looks like that's 0 and 6, the model is going to predict something completely different. In this case, 2 for the 0 and 0 for the 6, just by changing a few pixels. And similar, funny example here, where your image classifier of a pig adds a certain amount of very specified noise to that. It still looks like the same image to us, but your model's predicting something completely different. And you may want to be told if this is happening to your model. Okay, so I'm just going to go very quickly through a couple of things. Like concept drift also is more similar to outlier detection, but it's over a whole series. Is my training data changing over time? And then we've got a new library called Alibi Detect, which has just come out this week, which has state-of-the-art implementations of outlier detection, adversarial detection, and concept drift. And you can find that online, and it'd be great to get your feedback on that. So I'll just go for a very quick example on the Cypher 10 model for outlier detection. So this is a simple image classification model. It's just 10 different types of images. Basically, we've got it running here. So as we've got very close to time, I'll just go down to the actual examples. You've got a prediction here of a truck. When the model predicts correctly, it's a truck. And then you can basically, as we've got the outlier detection tied in, that will then go through and check whether this is outlier. It's correctly saying that's a not. It's going to just come out to the message dumper saying, no, this is not an outlier. We can then create an outlier prediction by adding some noise to the model, in this case, a little bit of noise to the left-hand corner. The actual model still says it's a truck, but you want to know that this is not actually part of the training data and should be highlighted. Again, with the outlier detection there running, it'll go through a few seconds later, and we'll get a prediction. In this case, the second example here in the logs, this is an outlier. So you can quickly find out this is happening. This could then go on to the alerting systems. So are we close to time? Yeah, okay. Yeah. So I think I'll just go back to the presentation, and we'll finish off. So we've shown you how you can add these things easily. There's also ones for adversarial detection in the demo and the slides, and you can go to those demos there for traffic signs and digits. And there's a great library from IBM on adversarial robustness 360. So we've shown you what you need to do to add certain things to your model, not just the model, but things you want to surround it with to really get a production-grade system, adding these things together. There's a list of the libraries that were all open source that you can use to actually achieve this. There's various other talks, including the one yesterday on KFServing, if you want to catch that up online, giving an introduction. And there's a group in LFAI called Trusted AI Community, which is working on this. How do you get this trusted ML models in production? And it'd be great to get your cooperation in that.
Thanks, Clive. If you guys have 5 minutes, I'll try and see, if the HTML detection works, and then just do a very quick demo if it does work, or I can probably, it's still not detection. It was just working 20 minutes ago. Can we just use certain links from your Slack? Maybe just show very quickly the pipelines part.
From Slack?
Yeah, I slacked you some links.
Right.
Let's just launch it, yeah.
It's time.
While we are doing this, if you have certain questions, you can bring it up, right? We can certainly tackle it.
There's nothing else on my Slack when I...
Just your private chat. Okay. So just in terms of the scenario, right, what we are trying to do here is, hopefully it loads. So this is, a typical model. It's a scikit-learn model. In this case, this model, essentially what it does is, it simulates shipping industry. The shipping industry carries your food items, right? As these food items are being carried, right, through airplanes, through sea, right, they might get spoiled, right? So because, they have different temperatures, carbon dioxide, nitrogen, CO2 level, right? So this model actually, is a scikit-learn model which is trained on that particular data set, these shipping containers which are coming in. And then there is, a pipeline, right, which in this case is a Kubeflow pipeline, which essentially will train that model, right, deploy that model using KFServing, launch a default and a canary version of it, and then, I'll probably, send some load from this side and then be able to show you, a few things. So for example, this is a typical Kubeflow pipeline, right, which you can launch. In this case, I do need to ping one more thing. Let me just get this, because I need to. Okay, so to launch this pipeline, I need, my model training code, which I just showed, right? And this is essentially in this GitHub repository. So let me just. Is it Command V, Control V? I have not used Windows in a while.
This is not Windows, this is Linux.
Can you paste it? Can you copy paste here, this one? Oops. Yeah, I think that's probably what we will do. I'm trying to do a copy paste, but it seems it's paste. Okay, that worked. Right, so I will just launch it now. So it just launches this pipeline, it will appear, and what you will see is, this one single pipeline, it will essentially go through all the different phases which we were talking about into the Kubeflow ecosystem as it comes up, right? So essentially, training the model, deploying the model, and then launching, default and a canary version of that model, right? So it's taking a bit of a while here. Yeah, we'll probably. I'm sorry about it, right? It's certain links are not working on this laptop. Yeah. But we'll record it and definitely share it your way. And this actually will show this end-to-end working in a pipeline context. With that, any questions anybody has?